early morning for some time zones. Okay. Oh, let me just share privately. I'm just talking to my family, okay, when I share this. So the reason I'm caring now about how many followers I have on LinkedIn is that will influence mine and Guy's book sales. It will help. And Greg was helping me because I thought, seems like I should have more followers, but I wasn't really following Greg's advice. And also the posts that Guy and I had been doing together, it took a lot of work to do those posts. Well, now I'm taking piece parts from what we're working on for the book anyway. And I just did a few things of making it simpler for people to follow me. Oh my. If I just extrapolate, I'm going up at about 2,000 to 3,000 followers a month, something crazy. So, but again, I just want to help the community, but it does matter to mine and Guy's book sales. So I'm kind of excited just sharing it with my family. Since that time I posted the 20,000, I'm also almost at, that was Monday. I'm almost at 2,500 now. It's just insane. And I was telling, next time Greg gives me advice about LinkedIn, I follow it. But it's just kind of funny. I could still be such an idiot, stubborn about what I do. Okay, let's go. Guy, if you can start recording.
We are live now.
Excellent. Hello, everyone. All right, we're going to just, I'll share, and we'll go over quantile transformer briefly again. I will always encourage you to do this when you're trying to learn something better. It's hard to see. Let me know that this says, yeah, it's showing great. To really understand this better, and I think the way to do it is when you look at these and you see something you don't know, make a toy example out of it. So for example, in this fit thing right here, play with that interp function. Obviously, it's a NumPy function. It's called interp. It's for linear interpolation. Here are my x's, my original x's and y's, and here are my new x's that I want to get new y's for. But Jonathan found a really good link here, and it's just helping you understand probability density functions and cumulative distribution functions. I was trying my best to make this really clear to you guys, and I was hoping you were getting it. But when you look at the probability distribution function, I'm trying to make a Gaussian curve here. Let's just review. This is the x, okay? And to get a specific probability off of that curve, I just plug in the x and I calculate or look up in a table the y value. Simple. However, if I want a cumulative distribution curve, how do I get that? I have to integrate with very small panels to say, well, I'm accumulating probability. Well, and I did have some plots above, but okay. A Gaussian curve looks roughly like this, right? If I add these up, that curve would start to look like this, and it would flatten out on this end. What's valuable about that is I can take value for a given x, it's the same x's. I could go up here above 1.5 and say, oh, if I want to go from the far left up to 1.5, that tells me the probability of getting values at 1.5 and below. But if I want the probability of values between 1.5 and say -1, I just have to take the value off that CDF and subtract the value off the CDF for -1. I just say this one minus this one, and I've got the cumulative probability of points lying between those 2 points. But we're using these principles in the quantile transformer. In this article, which I basically just added right here to the top of quantile transformer, it shows the principles of this quite clearly. And with using, I love it because it uses simple toy examples and it looks like crayon drawings, the best kind. So it goes into it in great detail. But again, to take a skewed distribution, like I showed y'all last week, if we go through this was the very silly toy example level. And then we got to a real big boy. When I show you, I went into excruciating detail on how to create a beta distribution and transform that to a Gaussian distribution and then create skewed data with it, but showing how quantile transforming will remap it to a Gaussian shape. And if you need to do this, quantile transforming is powerful, because not only will it scale your data, it will remap it to a Gaussian shape. So that's the key thing here. Okay, now I hope I'm not making y'all dizzy with all this scrolling.
Tom, just to add, correct me if I'm wrong, when we're looking at the cumulative distribution, one thing that came to mind while I was looking at everything, when you describe the curve where it goes up and then starts to flatten out, it reminds me a lot of when you're doing when you look at the RLC, the area under the curve. You see, when you look at that graph, you see that it goes up and then it flattens out at the top. To me, it's like the same line that's gaining.
So repose your question one more time. I want to make sure, or your statement.
Yeah. So when we look at the cumulative distribution probability, that the curve, it goes up and starts to curve and starts to flatten out.
Yes,
and when you have the area under the curve, when you have that graph plotted, it's doing the same thing. It's going up and it starts to curve and then it flattens out.
That's correct. That's exactly right. And if you think about that, you're plotting the integration of the PDF. And remember, I want y'all to just love integration conceptually. What is it? Every time it's just area under the curve. If you saw my LinkedIn post and that slide in my DSGO presentation, and I can pull that slide up, in fact, I showed, hey, if you want to derive velocity from just tracking the acceleration curve of any object, you have to add up the area in very small amount, like you add up to here. It's a running sum of the area under the curve to show what the velocity would be. You only have to know the initial velocity before you start doing that. And then you can integrate under the velocity curve to figure out the position. It's the same thing with the PDF. We're just adding up the small areas under the curve up to a certain point, and we take that much area and we plot that for the cumulative adding up distribution function. Okay. Whew. It's simple, it's just not easy. There's a lot of little steps that are understandable to quantile transformer. You can figure them all out, but dang. Okay. And by the way, if you're like, Man, I still don't understand quantile transformer. That's okay. We're going to show you something to help you realize it'd be super rare that you'd ever even want to use it. Now, I'm not saying you can't. You could just use it all the time. There would probably be no big deal in using it all the time. But why? I'll still use standard scalar most of the time, or min max or something else. I really like it when the data is balanced across zero and it goes equal amounts on each side of zero. I like that, or at least for the range. Okay, the normalizer. Let's look at this. So the normalizer is the last method we'll cover. And I love it because it reminds me of linear algebra, by the way. But let's look at what we do with it. Now, again, this is pure Python right here. We're not doing any NumPy. I love NumPy. I just taught a class for it with Hugo's class for Python. Look at this data mag number. How am I getting that? I'm going through each value in my data. By the way, is this large enough? Raise your hand if you want me to make this bigger. Okay, I'm going to make it bigger. Let me know when it's enough. That's one click. Is that enough? How about you, Sundeep? Is that a little bigger? Okay, one more. Is that good? Awesome. Okay, so I'm going through each point X in my data. This is a list comprehension. And then I'm going to square each of those values for X. I'm going to square each value of X, and then I'm going to sum all of them, and then I'm going to take the square root of that. That's just the Euclidean norm, right? If this was two values, it would be like a right triangle, and we're finding the hypotenuse. That's all that's going on here. So that data magnitude, now I'm going to go through each point X, and I'm just going to divide it by that Euclidean norm, and that's my data normalized. Now, if I was new to data science, but I had my engineering and linear algebra background still, my predictive analytics background from physics, and someone said, go scale this data for me, this is the one I would have thought to do, because it's very physicsy. It's very linear algebra like, it's just, oh yeah, let's take this is a giant vector, basically. That's the way it's viewing it. It's just a giant vector, and we're pretending that every value of X is orthogonal, meaning it's completely independent from all the other values. And we're just going to find the magnitude of this giant vector in hyperspace. We're just going to find how long it is. That's really what we're talking about. When I say hyperspace, I want y'all to feel good about that term. So I want to pause here. Would anyone like me to explain hyperspace more, what I mean by that? So please don't be shy.
Yeah.
Okay. Oh, what do you think, Jonathan?
Yeah, just do it.
Okay, I'm going to do it. Can you all visualize things in 2 dimensions? How about 3 dimensions? Some people struggle to visualize things in their mind in 3 dimensions, but here's my mouse. If I show it to you and I twirl it around a bit, you can figure out the 3D, right? Especially when you're off camera and you're looking things in your room, you see things in 3D. What about 4D? Oh, well, are you talking about time? Now I'm looking at something dynamically. It could be. What about 5 dimensions of space? Well, Tom, that doesn't exist. No, but it can exist mathematically. And what we're claiming mathematically is that all 5 of these dimensions are independent of one another. What if I had 1,000 dimensions? And I'm saying they're independent of one another. And I have ways to test for that they're independent of one another. That's hyperspace. We're just saying We're going to go beyond what you can visualize physically, and we're just going to believe it mathematically. So when I say hyperspace, I mean probably far more than 3 dimensions. Now, where is this important? It's hugely important in natural language processing. When you may be thinking, but I can't even imagine that it's possible for there to be that many variables that are truly independent of one another. Yeah, it is. It totally is. Because if you're turning language into space, let's say you're going to do it for each word in a group of documents. Every word is unique. And it can be closely related to other words spatially, but each word's unique and it's independent of the other words. And if we're going to turn, remember, all machine learning problems are math problems. We're going to turn language into numbers. They're going to be independent of one another. Now, I hope that helped. It's like, oh, wow, yeah. There can be a gigantic hyperspace where all of those rows that representing different variables are independent of one another. In fact, that's a big math machine I'm working on for my work. And it takes these technical documents and it I mean, literally, guys, I'm talking about a sparse matrix. That's a matrix with mostly zeros and a few values sprinkled here and there. It's literally the number of tokens in my document. It's like broken up to words, numbers, alpha characters, punctuation, you name it. And it's just creating this dumb tokenization. And so that's my rows. My columns are each document. The individual values in the matrix are just occurrence rates of those tokens for that document. After I build it, I can bring a new document in, tokenize it, and within under a half second, it can tell me which of those documents is the closest match to this new document I brought in. Lightning fast with NumPy. So yeah, hyperspace is a real thing. But I find the easiest way to visualize it and help others visualize it is with language. So that was a long way to get you comfortable with Euclidean norms being applied to hyperspaces, huge value sets. And that's why I like the normalizer, but what I'd really like to do, and by the way, this is totally legitimate, what I'm about to say. Take the normalizer, take this normalized data, find its mean or median, subtract that from all the numbers, and then just find a way. You could use standard deviation, but just find a way to spread it back out so it's equally balanced across 0 to some negative value and some positive value. Now, here's how you do that same thing with NumPy. First, this is just me saying I'm lazy. And if I sent you an array of data that's not a NumPy array, go ahead and convert it to a NumPy array. This is Tom being constructively lazy right here, right? If the type of data is not an MD array, make it one. And this is how, by the way, I could have done all of this in one line. I just decided to make it a little clearer, but I could have said the scale data equals the data divided by this. In fact, I could have done a divide equal right here and just called this data like that, and then return data. But I just was, oh, sorry. I was trying to make it clearer so that there's always options to the way you code something. but I show how to do it in pandas too. This is unnecessary. It's just a fun exercise at this point to say, okay, for each of the columns, scale it. And why would you do it here? Just so you could, if you wanted to use the normalizer, which I love, you could do it at the pandas level. But what's nice, look how you can do all this math to the whole column. That's what's brilliant about this. Then you see pandas just lets you get away with murder like NumPy does. You can do all this stuff in parallel. And then I take the square root of that stuff and then apply it back to the column. Well, the column name plus, look at all these liberties you can take with pandas. I'm creating a new column on the fly. I'm doing that step that we just did above. So let me walk through each of these. I've got just some temp column. And I'm going to get the square of the column, the current column I'm working at, as I cycle through all the columns. And then I sum that column. So I've got the squared sum. Again, this is a series because we're just working with one panda column. So that is a panda series. And then I take the square root of that. That's my Euclidean norm there, the magnitude of my vector. Now, for that same column, I'm just dividing all the values in it by this vector mag. Again, all this is made possible because pandas is built on top of NumPy and other things. Pandas brings in a lot of great tools. And then I don't want to keep extra columns hanging around, so I just drop it. But I just remind myself this is a unit vector for that column name. So it is a new column. It's the scaled one. And then I return the whole data frame after I've done that for all the columns. Okay, let's see how that acts on our data. I've got this fake distribution we've been using over and over. And then when I normalize it, now here's the thing though. Look at this small range of values. This is why I suggest that if you like the normalizer, go ahead and post-apply standard scaling to it. It'll be a really unique approach. You might, after you see it, you might go, oh, I should have just used standard scalar. But you could use some type of min-max or some type of just new scaling method. Again, it's just trying to get all of these on a level playing field. This is me just applying those functions we went through above with the pandas too. However, by the way, I hope, let me know if you don't know how to get access to this. This is in our pipeline class folder that we share on in Google Drive, the one that I've shared with y'all publicly. It's not the public directory, it's the class directory is what I mean. Okay, the normalized class is meant as a quick scaling method. What you'll find is there's two, in scikit-learn, there's a normalizer that actually uses the fit and the transform, but you might come across one that's not capital. It's just called normalize. Normalize is a subset of normalizer. You want to use normalizer, but I show this in case you come across normalize and you get confused. Okay. Now, I'm going to ask y'all to trust me on this. Garth and I are putting at least one type of hybrid scaling method in our book. You're not confined to use any of these scaling methods we've just shown. When I saw a power transformer, and I've used power transform scaling of different kinds before, and I thought about how much I love robust scalar, I combined the two. And I can't remember if I showed y'all that above, or I don't think we did it, but I just want y'all to know that that's a great thing to do is create some hybrid scaling method. So the normalizer is quite powerful in what it can do with outliers and stuff, but it can be a little scary too. There's a whole notebook I prepared on how the different scaling methods some are sensitive to outliers and some are not. But we're going to move on, and I'll share that with y'all in that in our course directory on Google Drive, just so you can see that. I'm wondering, well, yeah, I had something. I'm gonna just stick to my plan. I kind of wanted to show you all that now, but we're gonna go to something else, and I want to show y'all this other notebook here in a second. I'm just getting it ready. Making sure I got the right thing. Yeah, I do. Pull it over to where we're looking. Okay, now some of y'all may have seen my post on this on LinkedIn, and so if you have, you've seen this notebook already. But you will come across textbooks, and Ku, one of the top voices on LinkedIn that I'm friends with, he confirmed, yeah, Tom, I have one of those textbooks that says one of the conditions for linear regression is that you have normalized data. And I took a risk and really called BS to that on LinkedIn. And I invited people to say, please correct me if I'm wrong. Not only did everyone confirm, but I had some private messages saying, Tom, I think you're right, but I have textbooks that say the same. And then David Langer and some others said, I have no materials that have ever emphasized that normalized distributions of feature variables is important in linear regression. So there was a mixture. And then Jim Frost weighed in, a prominent statistician online. He's a really nice guy, has a really good blog and textbook that he sells. And he weighed in and said, you're right. And Gaith and I were already suspecting this, because I think Gaith and I would rather have uniform distributions of feature variables than Gaussian distributions, because then we can have confidence that we have an equal amount of values across the entire range of the feature variables. So this is an experiment I did. First, I just create a random normal distribution. And because it's a small number of points, you see that it hasn't really filled this out yet. Now, just to give you a feel by what I mean by that, let's do this. If I sample 4,000, it's taking longer. Uh-oh. I don't know what happened. I don't know how I ever had this working before. I must have copied this from some other place, so I'll fix that. Well, this is horribly inadequate. I'm going to go grab from another. I think I must have pulled the pieces of that from another notebook and forgot to rerun it just to make sure everything was there. Go up this way, so it might take less time. Sorry for the wait, guys. When you watch me correct my notebook. Surely it would be here and always visualizing. Embarrassing. There we go. That's what I'm looking for. I'm going to get all these just in case. I don't think I need the others, but we'll use it. And now I have pandas in case I need it. Surely it'll run this time. Yes. So you can see it. Well, oh, if I use 4,000, now it's looking more shapely. And if I break this down into finer bars, buckets, it'll look more Gaussian. But I'm just using a toy data set here when I do it this way. Now, an important plot. This is just a way to make sure that we're seeing data that is Gaussian distributed. So the closer our points align to this theoretical 45-degree line, the more Gaussian our data is. But when we're working with sample sets, it's never going to be perfectly aligned to. We're just looking for it to be closely aligned. And so here is just my, we create our fake labels. There are probably some overlapping points we cannot see. So we're just looking at X versus Y. And again, no surprise, right? And no noise. So we're just making sure, by the way, this is just that we created the X again. I'm trying to remember where we got X from. This again, I'm not going to rerun anything for fear. So it was just a uniformly distributed set of basically just a range function to create X. Now, again, this is something you guys might do to experiment to understand the principle better. But here I had a real question. Now I went straight to modeling because there was nothing horribly complicated going on here with this fake data. And I ran a linear regression. And before I sent it in, I just made sure it was NumPy stuff and shaped accordingly. And it's just univariate, so that's why I'm only doing one column here. And so I fit the model with these NumPy arrays, and I found my slope. Yes, it recaptured my slope fine. And so we plot our predictions and we see they exactly match. So we're going to repeat all those steps, but we're going to use, that was a Gaussian distribution. We're going to use a uniform distribution this time. And let's check something real quick. Sorry for scrolling so much. I'm just wondering what the heck I did here. Really, I should have said somewhere that X equals data dot values. So that's probably what I did and failed to put it in here. So I'll make sure this works before I copy it to our course Google Drive folder. But this time, we're going to use a uniform distribution instead. So again, if I amp this up, we're going to see more of a flat. But for this range that I chose, only 40 points, no big deal. Well, now look at the QQ plot, and it's clearly got some weaknesses, but it's not that bad. And then I can see that, yeah, that roughly looks like that, the distribution of points from above. That part looks like it would actually work. And then I do the regression again, and I see I get a really good fit. I mean, I used a Gaussian distribution, and this time a uniform distribution. And I'm not even worried about running metrics because it's obvious they're just adequate fits. So now I'm just trying. I use just one of these at a time, and we probably can run these. I've got either a uniform, a normal, or a beta. And I'm just seeing if I run these different ways, and this is just a way to make these betas look more like these because the beta just goes from 0 to 1. I just want to see if can I get good fit for all of those. So each time I only pick one of these cells, and then I run through the rest of them. So I look at the histogram. I create the same amount of noise for each one. I create my fake data, and it's these weights that I hope to recover. Okay, and so I've got my noise. I look for the max of Y, and I create some noise on that. So I'm actually adding noise to the distribution data too. And I go ahead and do a fit each time. So I would run through each of those. And here's the record. If I use the uniform random data without Y noise, I get the exact weights. If I do the normal random data without noise, I get the same weights. If I use the beta, I get the same weights. This is just having a markdown challenge. There we go. Now, add noise. Uniform random data with Y noise. You can see that they all did pretty well with the noise included. They didn't get the exact weights, but again, I've got noise. So the conclusion from those experiments is we need adequate data across the numerical range we wish to train over for each feature. But the distribution shape is not as critical as some references make it out to be. And in fact, when Gaita and I had a very serious talk about this, I don't mean like we were arguing. We were like the Wright brothers in agreement mode. We were realizing, you know what? If you did use something like quantile transforming just to remap to Gaussian, isn't that somewhat of a falsification? Now, you might ask, well, when we scale data, aren't we falsifying? Would you say if I report something in feet versus miles, or meters versus kilometers versus centimeters versus millimeters, is that falsification? No, not as long as I list the units. Then anyone can put it back to the other units. When we scale our values, we're not changing the essential way they're distributed. We're just getting them all at equal numerical ranges so the math plays well, so that we can interpret the feature weights after we've trained. That's quite a bit different than changing the shape of the distribution. So, but I would even argue, as long as you report that you've changed the shape of the distribution and you do it consistently, that's not a problem. It's just like reporting your units. Report your method of scaling, no problem. It's always, you take out an outlier, report that you took it out and say why, or go get it fixed at its source. But the point being, to say that normally distributed feature variables are important to linear regression, no, wrong. It's okay for you guys to question things that you come across in data science, but do it respectfully, kindly, and make sure you test the dookie out of it. In fact, I released this to a group of friends before I put it on LinkedIn, just to make sure I'd get some support in case some people lashed out at me. And I ended up being quite safe. And this is another guy that bravely reported that that's wrong. I was like happy to find some other guy that backed that up. So I'd like to pause here for questions, and while I'm waiting for your questions, I'll try to go fix what I think is wrong with with this notebook and make sure everything runs for you. So what do y'all think? Any questions here, or is that perfectly clear? Oh, I don't even need to say that. Just say x equals data. It's not a data. Okay, I'm just gonna I'll go through some runs of this while I'm waiting for you to ask questions. It's okay if you don't ask questions, but while I'm waiting, I'll just run through this. And it might also help, see what I did there. If you just tell me, hey, this is perfectly clear, or please don't be shy about saying, oh, I really didn't understand that particular point. So help me out there, whether this was clear, helpful or not, an unnecessary detour on our learning.
Tom, we do have one. Keishan would like the link to the Google Drive to share with him the document.
Yes. What I will do is, that one. Yes, I will make a copy of this and put it. Oh, I'm sorry. You're saying you don't have the link.
Yeah, for the one that we're going through.
So basically, it's our class Google Drive link. It's actually more public than other stuff we have. And so I'm sharing the whole directory with you in the chat. I apologize. I thought everyone had it by now, and it's okay if you didn't. There you go. It's there. That'll get you to a lot of other folders. And yeah, it's I think it's okay for y'all to look at all of this. But the main one is this one right here. And I'll get this working. I need to import the linear regression. I just don't have it. I probably could type it from memory. I just don't have it memorized. And then I'll make sure this whole notebook runs, and I'll put a copy of it in our Google Drive class folder, or that one that I just showed y'all. But it'll specifically go into this one. This is where we're at right now. We're in this file right now. And then when I find that other one that